All right, section 9.3, we're going to continue looking at convergence. But we're going to see something happening in this section that's distinctly different than the last section. And what's going to happen is we're not any longer, at least not necessarily, going to be able to find out what a sequence or a series, converges to. So in general, we don't always need to know whether or not a series converges to a specific value. We just want to know that it does, in fact, converge to a specific value. So generally speaking, we're wanting to be able to test to see if a series will converge without actually finding its sum. And we have, I think it's 3 different tests in this section for how we can do that. Kind of like in the last section, some tests work better on certain series than others. Now when you get to the homework, it's not going to tell you which test to use where. So you're going to have to be able to look at there and look at the series that you're given and decide, what might I try? This is kind of like with integration, right? And you try it, and if it works, then you chose well, and if it doesn't work, then you try something else. So that's going to be the name of the game for this particular section, is learning how to make a good decision when you're looking at a particular series. Now the first test we're going to look at is called the integral test. It's Theorem 3.1. The idea with the integral test is that if the integral from 1 to infinity of the function that would be the equivalent of the sequence converges, then the series with that sequence in it will converge. And if that integral diverges, then the series would diverge. So you might want to be thinking when you're looking at these problems, can I find the integral of this quickly, easily? Is this something that I can do an integration for without a lot of effort? Or maybe, if not without a lot of effort, some method that I know and know well how to process through. Okay? So this is one of our 3 tests. So if you take a look at the first example, example number 1, we have a series. The series is going from k equal 2 to infinity, and it's 2 over k ln k. This one just beckons us to use integral test because of that ln of k. And because of that ln of k with the k in the denominator as well, what are you thinking we should do from integration? Do y'all remember? Use substitution, definitely. So what we're going to do, let me first actually write down the integration that we're going to be working on. We're going to attempt to do the integral from 2 to infinity of 2 over, and then we're turning all the k's into x's, x ln x dx. And just as you said, this is actually going to be a u substitution. So what should u be? U is ln of x, which means that du is 1 over x dx. And because of all the mess that I'm going to do later, I want to actually change my limits of integration, which is not something I really ever do in Calc 2. It's just seldom helpful. But because we're going to be doing so much else with this later, I'm going to go ahead and do this now. So what that means is that if x is equal to 2, then u would be equal to ln of 2, right? And if x, I'm not going to say equals infinity because of course that doesn't make sense since infinity is not a value, but if x is approaching infinity, then u, which is ln of x, also approaches infinity. So when I'm rewriting this, the infinity still stays at the top because it's still going to be approaching infinity, but the lower limit is going to be ln of 2. Is everybody okay with that? I'm about to put things in terms of u. This over x part and the dx part, that's the du. The 2 stays, and then my ln of x is actually my value of u. All right, so I'm going to pause real quick and remind you that there's something that nobody has done yet. I think Ben's the only one that's actually even talked to me about it. Do you know what you haven't done yet? Yeah. Out online, if you haven't already checked out our Moodle Room site, which you should have because you should be printing off these notes, there are 4 documents inside of the basic skills, folder, I guess, or whatever. One's for derivatives and the other's for antiderivatives. It's practice. be a good idea for you in the next couple of days over the weekend before you come see me, because you've got this 5-day break before you see me again, to print out those sheets and start taking a look at that, reviewing that. Because before the first exam, you need to come in and you need to take a derivatives quiz and you need to take an anti-derivatives quiz. And you need to take each of them at least once, because otherwise those turn into grades of 0. But if you don't get a grade that you want, you can retake it up to 3 times. So you can take it a total of 4 times for each quiz. But you only do it once a day, and we've only got until the first exam that you need to make sure you take care of that. Okay, does everybody know what I'm talking about? Okay, good deal. So make sure that you get on Moodle Rooms, print those out. The 4 documents are, again, there's 2 documents for derivatives because it's the questions, and then there's a document that has the answers in them, solutions in them. Same thing for anti-derivatives. If you'll remember, there's no need to simplify anything, so you will see that the solutions on there are not in simplified form. Okay. All right. There's a couple of things going on here. One issue going on here is that I've got an infinity as a limit, right? Limit of my integration. And so that's not something you deal with all that often, or haven't dealt with all that often. So let me remind you what you do when you deal with that. When you have that limit as infinity, you need to replace it with a notational limit. Oops. So you rewrite the infinity at the top as, your book tends to use n. That's pretty typical, but you could use another letter if it starts to confuse you, because we've got natural log here that's going to have an n as involved as well. But we want the limit as n goes to infinity of the integral from, in this case, ln of 2 up to n of 2 over u du. We're going to continue to write the limit until we plug in the limit value, as you well know. But right now what I need is I need the integration of 2 over u. So what's the antiderivative of 2 over u? 2 ln of u. And it's technically absolute values of u. My u values are actually all positive, so I can sort of avoid writing the absolute values on this one. It won't hurt anything. And I need to evaluate that at n and at ln of 2. So my limit as n goes to infinity of 2 ln, this is why I said n's a little bit awkward here, 2 ln n minus 2 ln of the natural log of 2. So the natural log of the natural log of 2. So far, so good? All right, so what in the world, I don't ever have to actually plug n back in as x. The reason I don't is because I changed those limits of integration to be in terms of u's. Do you remember doing that? Okay, so you see the ln of 2 here happening instead of 2. Okay. So we don't have to turn this back into x. If you decide not to change your limit of integration, you need to turn it back into x and then plug in the 2 in the infinity, or the 2 in the n for infinity. All right, so let me just make a comment right now that this may be looking like an ugly expression that you really wouldn't want to evaluate, and that's perhaps a true statement. But you don't really have to evaluate it. The point being right now that 2 ln of the natural log of 2, or the 2 natural log of the natural log of 2, is simply a number. Agreed? Your calculator could give you a decimal approximation if you wanted to. But the point being is that this has a numerical expression. Of bigger concern to this particular problem is this portion. The limit as n goes to infinity of 2 ln, or 2 natural log of n. So what in the world is the limit of 2 natural log of n? What happens? Don't have to use e. No. Okay, so the function itself approaches infinity, right? So the graph of natural log, I drew a sketch briefly, I think, last time that we did this, is the natural log graph looks like this. So as you take the x value going to infinity on this particular graph, the y value goes to infinity as well. It does it super slow, right? Natural logs don't go up very quickly, but it still continues to increase without bound. There is no stopping spot for where it stops increasing. So this part that I've boxed in this purple color right here is actually infinity. It does not stop increasing. It will continue to increase indefinitely. So when I take infinity and I subtract away a number, which is essentially what this happens to say, what is that? It's still infinity, right? I've taken something that's infinite and I've subtracted away a finite amount. Well, this is infinity. So this integral right here from 2 to infinity of 1 over x natural log of x dx diverges. That's what you just found out by finding out that the limit and doing all of that processing was infinity. And so since this diverges by the integral test, the one we just did, that one we just learned about, the integral test, the summation from k equals 2 to infinity of 1 over k ln k, what can we say? It also diverges. Now, it's worth pointing out that if we had gotten a numerical value, if over here, instead of this saying at the end infinity as the value, and it actually said something like 7, or even something ugly, meaning it has some ugly expression, that would tell us it converged, correct? And the integral test would then tell us that that means that the original series also converged. But there is nothing in this argument that says what it converges to. It would not converge to the same value. Okay? So the value that I'm getting down here at the bottom, if I do indeed get a value, does not actually translate to being the value of the series either. That doesn't happen. All it does is it tells you that the series converges. Everybody clear on that? Okay, let's take a look at another test. Oh, I was wrong. There's 4 tests in this section. I forgot about the p-series test. P-series test is probably one of the cleanest, simplest ones, even better than the geometric series that you guys did last time. P-series simply says that if I have the summation of 1 over k to the p, that it will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. And that's it. Very simple, very clean. The reason it maybe is a little bit simpler than geometric is simply that geometric has that additional condition that tells you what it converges to. This one doesn't have that, because otherwise they're very equivalent in terms of how difficult they are to process. So let's take a look at this particular series. This one is a series from k equals 6 to infinity of 4 over the square root of k. The first thing I might want to make mention of is that this doesn't exactly look like that previous slide. It doesn't look like I have k to a power in the denominator. But that doesn't mean it couldn't look like that if I do a little bit of rewriting. So do you remember how we can rewrite this so that in fact it does look like k to some power in the denominator? Right, very good. So the square root is equivalent to a power of 1/2. That's it. So, will this converge or diverge? This diverges. Why? Yeah, because the p, which equals 1/2, is less than or equal to 1. And let me actually put in here what test we were using. This diverges by p-series test. Because the p is equal to 1/2, which is less than or equal to 1. Compared to the last one, that was a lot less work, right? So I like the p-series test because it's so quick. It's a nice one. Yes?
So this one, it doesn't matter if p starts at 6 or 1?
It doesn't, and it really didn't in the other one either in terms of convergence.
Just
where that came into play was in what the summation was actually equal to. Yeah. And that's actually going to be really, that's a good point to mention, Tally, because in this entire section 9.3, it doesn't matter where k starts, because we're not going to be finding any summation values anyway. We're just going to be saying whether they converge or diverge. Yeah, good point. All right, let's do another one, comparison test. Theorem 3.3, the comparison test says that if I have two sequences and one is smaller than the other one, so AK is smaller or equal to BK, and we find out that the bigger one converges, okay, so notice where you're doing this. They're saying this one converges, the series with that one in it converges. Well, then the smaller one would be too. It would also converge. And this is a direct throwback into the squeeze theorem, right? The 0 for sure is converging because it's already a constant. So if the BK converges, then the one that's trapped between there is also going to converge. It's just an application of the squeeze theorem. And likewise, we could actually talk about if we knew that the smaller one, that is if we knew that AK right here, if this one diverges, if it goes to infinity, and I've got something that's larger than it, well, obviously it would go to infinity as well. Okay? So it seems like a very reasonable argument. What's trickier is sometimes making sure on which one's actually smaller or bigger. And so obviously I'm doing an example next that works with this, and you've seen me do this kind of an argument before, and you've done arguments like this before too back in 9.1. But what we're going to do is we're going to actually try to create a sequence that really is very close to what we have and decide if it's bigger or smaller. So when we're looking at these particular sequences, in general, what we're looking at is we're looking at the largest exponent terms, because they're the ones that are dominating what the whole expression is doing, especially on the end values. And in this case, we're talking about the end values as we go to infinity. So on the very end of this graph, the part of this that's affecting what happens to my y value, if you will, the most on like a graph, is going to be the k squared and the k cubed. Everybody with me so far? So this is roughly equal to, okay, this is what I'm sort of thinking. This isn't work of what we're writing down, but this is roughly equal to k squared over k cubed, which is equivalent to what? 1 over k, right? K squared over k cubed is 1 over k. So this series, the sequence inside of this series, this sequence of k squared plus 1 over k cubed minus 3k minus 2, this is going to be on the end of this graph. It's going to look a lot like the sequence 1 over k. So that 1 over k is going to be the other sequence that I'm going to use to compare this. But you know what happens to 1 over k. We've talked about it last class period. It's called the harmonic sequence, the harmonic series. And then we have actually talked about the p series over here, which we could also use to talk about this. What happens if p is equal to 1? It diverges. And I actually showed you another argument of why it diverged last time. Remember it had rectangles in it? You guys remember that? So this sequence right here of 1 over k is going to diverge. Agreed? So my expectation is that the sequence k squared plus 1 over k cubed minus 3k minus 2, that will also diverge. Because if one diverges, the other one should as well. I just have to make sure that the 1 over k is actually smaller than what I have before. Okay, because that's the condition upon which that this whole theorem was built, is that if the smaller one diverges, so does the bigger one. Make sense? All right, so let's take a look. This one will work, and it will work very nicely, but let's argue through why that's happening. So I've got k squared plus 1 over k cubed minus 3k minus 2. So the first thing I want to do is I want to notice that this value is bigger than if I removed the plus 1 off the numerator. Why? Numerator is smaller. So if the numerator is smaller, then the fraction is smaller, right? So this works, no problem. But I also want to remove the minus 3k and the minus 2 off the denominator. So why in the world, if I remove the minus 3k and the minus 2, do I still have a smaller fraction? The denominator would be bigger because I had subtraction in it, right? This minus 3k and this minus 2 were making the denominator smaller, and now I've created something that doesn't have that, so the denominator is now bigger. Bigger denominator, smaller fraction. So this sequence right here now is exactly the 1 over k I was expecting to have when we sort of made the argument above in red. Okay? So let's actually write out what we've found, the pieces all together. So we know that the summation from k equals 2 to infinity of 1 over k diverges. And there's several reasons you could cite why. So tell me something I could say. Why could I say that this diverges? What's one reason? By the p series, okay? By the p series because p equals 1. Okay? You could also say because it's a harmonic series. We've dealt with the harmonic series as its own issue all by itself before. That would be fine. All right, so we'll say, and we'll do it this way. 1 over k is less than k squared plus 1 over k cubed minus 3k minus 2. And we'll throw in the zeroed less than just because it was part of the, was part of the original conditions set forth. It's definitely less than because the k values are positive values. All right. So then by the comparison test, whoops, since the summation from k equals 2 to infinity of 1 over k diverges, so will the summation from k equals 2 to infinity of k squared plus 1 over k cubed minus 3k minus 2. You're going to have to write down some logical argument here. Okay, complete sentence it doesn't have to be. But you do have to write down the justification for why you know something's going to converge or diverge. I'd prefer you state, for instance, comparison test as opposed to stating theorem 3.3, because theorem 3.3 is specific to your book, whereas comparison test is a universal, name for this particular process. But if you don't, it's okay. Any questions on this one? All right. Let me show you. I'm going to actually jump ahead. I want you to flip ahead to the last page. And I want you to take a look at this particular last example. And I want to talk about why this last example is more complicated. And it isn't simply because it has 3 terms on top or something like that. That's not why. Why in the world is this particular example not going to work very well with the comparison test? What is it about this example?
The bottom has addition.
Yeah, the denominator has addition in it instead of subtraction. Right? I mean, that was very nice on the last one, that I could still just sort of string these less than or equal to kind of equalities along, because I happen to have subtraction in the denominator and addition in the numerator. But the reality is that whether there's addition or subtraction, this particular problem is still dominated by the k cubed and the k to the 5th, right? I mean, that's still what it overall looks like toward the end of the graph, whether there's addition or subtraction, you which way you go. So another test that's a comparison test that's a little bit easier to use in general, because I don't have to worry about these less than or equal to kind of inequalities and making sure I'm really bigger than what I had before, is called the limit comparison test. So previous slide, sorry. So we've got 2 sequences, just like with the comparison test, AK and BK. And the ratio of them, AK over BK, actually has a limit. And the limit is something bigger than 0. Okay, so we're going to take 2 sequences that are roughly the same, or that we anticipate to be roughly the same, and we're going to find the limit of that ratio. And if that limit is something that's bigger than 0, then if one of the sequences converges, so does the other. And if one of the sequences diverges, so does the other. Notice, if the limit actually were equal to 0, this test would prove unhelpful, right? Because it doesn't tell us what happens if L equals 0. So if you end up doing this test and you get L is equal to 0, either you've made a mistake in doing the limit, or this test isn't the right test. Okay, is everybody good? Makes sense with the process? The very nice thing about this is that I don't have to worry about stringing these inequalities and making sure that one's smaller than the other. But instead I get to do a limit process, which means there's a little bit more work with the limiting process too. So. All right, well, let's take a look at example 4. We're looking at whether this series converges or diverges, just like with the others. And like we said, that this is roughly going to be k cubed over k to the 5th, because those are the terms of highest degree. And k cubed over k to the 5th is what? 1 over k squared. So our comparison sequence is 1 over k squared. So it really doesn't matter whether you call the first one AK and the second one that I just created 1 over k squared, this one BK, or vice versa. It makes no difference. We just need to make the decision. I'm going to call the second one that we created the BK, and we're going to call this first one over here AK. Right, so again, it doesn't make a difference which one you call what, but I'm going to call the first one AK and the one that we just created BK. And so we're going to take the limit as k goes to infinity of AK over BK. In other words, the limit as k goes to infinity of k cubed plus 2k plus 3 over k to the fifth plus 2k squared plus 4. And all of this is over 1 over k squared. Okay, so mathematics that you know before tells you that if you have a fraction on top of a fraction, you can multiply by the reciprocal, right? And the reciprocal of 1 over k squared is simply k squared. So this becomes the limit as k goes to infinity of k to the fifth plus 2k cubed plus 3k squared over k to the fifth plus 2k squared plus 4. What do you do next? Now we're back into what we learned to do in 9.1 and what you learned to do ages ago as well, for that matter. What do you do to find this limit? Perfect, thank you, Jordan. So we're going to multiply by 1 over k to the fifth. And when we do that, we're going to end up with the first terms in each of them, which are the k to the fifths, becoming constants. So we end up getting the limit as k goes to infinity of 1 plus 2 over k squared plus 3 over k to the fifth all over 1 plus 2 over k cubed plus 4 over k to the fifth. And everything currently that's in fractional form approaches 0 as k goes to infinity, right? Agreed? As k goes to infinity, all 4 of these fractions here go to 0. Which means I'm left with the limit value of 1. And, yay, 1 is bigger than 0 today and tomorrow. Right? All right. So this is good. We actually were able to sort of satisfy that first condition, coming back here. We have this limit of ak over bk. The limit has a value of 1, and that 1 is bigger than 0. So the limit comparison test tells us then that either both of these sequences converge or both of them diverge. So the first one was the one we were trying to find information about, and we were trying to do it based on the second one. The second one is a series that we know something about. The summation from k equals, was this one 2? No, it was 6. From k equals 6 to infinity of 1 over k squared, what does it do? Converge or diverge? It converges. Why?
Do the p-series test.
It converges by a p-series test. The p equals 2, which is greater than 1. So the summation of from k equals 6 to infinity of k cubed plus 2k plus 3 over k to the fifth plus 2k squared plus 4 also converges. Why? Yes. Exactly, by the limit comparison test. Limit comparison test, like you said, says they either both converge or diverge. Since we found out that the one that we were comparing it to converged, and it had this property that the ratio was equal to 1, then the limit of the one the series that we were looking at originally will also converge. Any questions on that? All right.